Thank you. It's a real honour again to be elected to the Academy of Sciences amongst all these wonderful fellows here. My area has been in the development of energy materials, and why is that? Because I think the transitioning from a fossil fuel-based energy generation society to a renewable energy generation society is so important if we're going to save our Earth, if we're going to save our coral reefs that we heard about today, if we're going to stop the Antarctic ice shelf melting, we need to look at alternative energies. In Australia, we are certainly well placed for such a transition. We have lots of sun, lots of wind, certainly in Canberra, and certainly in Deakin, where I am in Victoria, and also wave energy. And yet we're still quite slow in the uptake. And part of the impediment for this is the lack of really efficient, cheap, safe energy storage, batteries, for example. So my journey in this area began in 1990 when, as a young, bright-eyed postdoctoral fellow, I went to Northwestern University to work on polyethylene oxide conductors, which are solid-state electrolytes for lithium metal and sodium batteries. That was the aim back then. At that time also there was a big push in the US or around the world, but in California there was a mandate that electric vehicles would have to zero emissions, vehicles would have to be 100% in California, and of course we haven't got there yet. Also around the same time, Sony released its first lithium-ion battery based on organic solvents that we all have now in our portable electronics, in our mobile phones and our computers. It's changed our life. And now, of course, there's a push to use those similar technologies in larger scale applications. That has some concerns in the sense that we are looking at quite volatile, potentially dangerous and explosive solvents in these batteries. And so if we're going to really upscale, we need to look at alternative materials, and that's really where my group and my effort has been focused over the last 20, 25 years. Certainly, that early work in the polyethylene oxide world has now borne fruit, and there's a company called Bolloré Group, also sold as Blue Solution, the blue vehicles, that have quite a number of these little vehicles running around Paris and Brussels and other parts of Europe based on the polyethylene oxide technology that I was researching way back when in 1990, in the 90s. Moving forwards to why we want to look at alternative energy, why we need energy storage for renewable energy. I think we all know the sun doesn't always shine, the wind doesn't always blow, and this creates a problem because we don't have a constant supply of energy. So we need to have, batteries are one option for us to utilise to try and level out these oscillations in the generation with renewables. So how does a lithium-ion battery work, or lithium battery work? You need to have electrodes, an anode and a cathode. You need to have an electrolyte. It's this thing in the middle here that my group has been working on for the last couple of decades, and also understanding the interface between the electrolyte and the electrodes. This thing in the middle here has to be highly conductive, but it also has to be stable, electrochemically stable, thermally stable, and also mechanically robust in order to be able to separate the two electrodes. And if we have the right electrolyte, then we're able to have utilise electrode materials which would allow us to have higher energy density, which means you can run your battery for longer, run your car for longer between charges. So one of the materials that we've been working on since the mid-1990s are ionic liquids, and these are materials that are basically composed entirely of ions, ion pairs, which means that they have very low volatility, or can be designed to have very low volatility. They have close to zero flammability. So here's a typical organic solvent that's in your current lithium-ion battery. If you blow a torch ionic liquids, it won't catch fire. This is a good thing, of course, if you want to have put this into your battery. The other positive thing about these are that they have very large electrochemical windows. So water has an electrochemical window of 1 volt. If you have certain ionic liquids that we work with, we design, can have up to 5 or 6 volts. This allows us to use materials as electrodes that require this high electrochemical stability, which gives us, again, higher voltage batteries, which means more energy density, longer lasting, etc. As well as ionic liquids, one of the areas I want to focus on for the next few minutes is the solid-state cousins, as I call them, of ionic liquids. They're called plastic crystal solid electrolytes. These are crystalline solids based on the chemical species that are in these solids are the same as in the ionic liquids. These are large, hairy cations with a positive charge on ammonium or phosphonium, are buried surrounded by the alkyl chains, and they're coupled to anions such as symmetric anions like PF6 or VF4. This is the one that's currently in your battery, PF6, lithium PF6. We've been developing more delocalized anions like bistriflamide, fluorosulfonamide, DCA, this boomerang molecule, which means that the coulombic interactions between the cation and the anion are quite weak. This leads to the inability to freeze, i.e. the ionic liquid, and if it does freeze, you end up having these a lot of dynamics within the solid state which allow you to have high conductivity. So my group's been looking at characterising, understanding these materials, understanding how we can control the dynamics using a number of techniques. So here we have a typical a material which has, it's crystalline in the lowest temperature phase. It's a crystalline material. We've got single crystals, we've got crystal structure from these materials. As you heat the material up, you go through a number of phase transitions, these thermal phase transitions, and each time you go through a transition, something happens to the molecules in this crystal. You start to get dynamics initially of this is PF6 anions are moving at a small amount of dynamics in the cation. As you go through to higher temperatures, more dynamics. Eventually, in the highest state, highest temperature phases before the melt, you actually have diffusion occurring. This diffusion is what leads to the high ionic conductivity that you get for these materials. High ionic conductivity is what's needed, remember, for a device. But the materials themselves aren't very useful in a lithium or a sodium or any other battery unless they're doped with a dopant ion that you need. So if it's a lithium battery, you need a lithium ion in there to be moving through your system. If it's a sodium ion. So we want to understand how to control that conductivity. And when we dope these materials, we end up finding that you can change the morphology, and sometimes you get, for example, these grain boundaries, and we want to know, is the conduction occurring through the grain boundary phases? Is it occurring in the bulk? Is it occurring due to vacancy motion? What is the nature of the ion association when you add the lithium or the sodium? How does these ions move? And we want to know this so we can optimise the materials to be able to put them into devices. And we're still working on that now. We don't have the answers, and every material seems to be quite different, so we have to really throw at all our techniques like crystallography, NMR, modelling to understand what's going on here. In addition to the ionic liquids and the plastic crystal materials we've been working on, my group has also still had an arm in the polymer electrolyte area. So not polyethylene oxide, the old material which is currently in the batteries that people have in the Bolero cars, but we're trying to make materials where the only ion that actually can be transported is the ion of interest. So the lithium ion, for example, lithium battery, the proton if you're looking for a fuel cell, the sodium if you're looking for a sodium battery. And the reason for this is if you have, in the polyethylene oxide materials, it turns out actually the dominant charge carrier is the anion, and that's not so good if you are putting that into a battery, because you can, with time, you could end up destroying or polarising your battery, which is not a good thing. So if we're able to stop the anion from moving by tethering it to the backbone and have the cation being the dominant charge carrier, whoops, that was a bit slow there, dominant charge carrier, then that would be a good thing for devices. The problem with this is that with these materials, those cations are very tightly bound to the polymer backbone. And this is a problem because you need to remove them to get them to conduct. So we've been looking at designing materials where we can create structures which allow ions to hop and be decoupled from the anion on the backbone. And that's what my group has been currently working on, and we've just been developing some new materials with the CSIRO actually to try and put these into hopefully lithium battery devices in the future. One of the main threads throughout my research career has been NMR research, using NMR spectroscopy and characterisation to understand dynamics and structure in these materials. And I have a great young group of people at Deakin and some great solid-state facilities to actually do this research. So we look at developing new techniques to understand ion, much like the protein crystallographers do, try to understand how the ion association occurs in these materials and how we can optimise that to get maximum conductivity. We do diffusion measurements to understand how we can design materials to have perhaps channels within the polymer material to optimise conductivity together with the mechanical properties. And we've also been developing in situ MRI, so magnetic resonance imaging, much like MRI of the body, but now for materials, to try and understand how phase transitions influence the morphology and influence the conduction pathways. For example, in plastic crystals, we've discovered that we can actually get oriented domains of ordered regions with disorder between these regions where the ions can conduct. We can use that knowledge to try and optimise these materials, and we can also do the in situ MRI where we have a device in the magnet, and we can actually cycle the device in the magnet and look to see how that cycling influences the material properties and the interfaces. And with this knowledge, we hope to try and optimise the materials and hence the energy storage possibilities. So I think energy storage is crucial for our future, for being able to integrate renewables, to have electric vehicles. Materials are still required to optimise energy storage. We still need to get better anodes, better cathodes and better electrolytes, and we still need to be able to optimise the interfaces between those independent components. And so that's going to be a long path ahead of us still, but I'm very hopeful that we'll be able to achieve the right solution ultimately. So I'm actually quick. So finally, I want to thank an amazing group of people that I've worked with over the years. This is the group currently at Deakin, but also we have a lot of international visitors, emeritus thinkers in residence, we call them at Deakin, and retired people who come and work with us. And I'm very, very blessed to have worked with those people. And I want to thank all these people and all my mentors, in particular Doug McFarlane, who I work with at Monash University very closely. And I want to thank you for your attention.
Thank you, Maria, for being ahead of time. It's always nice to have these things. And Mike DePeter there, please.
Week and Space Technology recently pointed out that in order to get fully electric aircraft, you would need energy densities about 100 times higher than what's currently available. Do you think that's even conceivable?
100 times. Certainly the current capacities that are in the devices that we have are of the order of hundreds of milliamp hours per gram. I think we can probably achieve thousands. That's a factor of 10. A factor of 100 might be a hard ask, but you might be able to have some of the components electrified and still use the fossil fuels for the really important bit, getting the plane up into the air.
Well, they talk about hybrid.
Exactly, and that's going to be, yeah, I agree.
Are there any further questions or comments, Marion?
Question slightly out of left field, but I wondered if you could comment about organic solvents and complex ions, which are potentially environmentally toxic, but nonetheless have potential very high utility. What is your opinion on?
In terms of the organic solvents or the...
Well, in terms of generally the molecules that are being constructed where we don't necessarily know about their environmental influences.
Sure, and I guess in terms of the new electrolyte materials that we're working with, one of the ideas is a lot of them are greener, which means they're more environmentally safe. But of course, everything has its maximum tolerance. I can't answer it in terms of exactly how toxic or not, or otherwise they are, though, sorry.
Last question, Bob Williamson.
So it's really a version of Mike's question. Is there actually a theoretical limit to the energy density you can store electrochemically?
Gosh, difficult question. I don't know the answer to that, but I do know that every day and every week there are so many different types of technologies being developed. So we've had lithium ion now for decades. People looking at lithium sulfur, lithium metal. Of course, lithium being very, very light means you get more energy density. That's why lithium, right? Fuel cells as well. I mean, the hydrogen is an incredibly light element. So people are looking at lithium air, where you don't have to worry about carrying your fuel with you. So there's a lot going on in trying to optimise the energy density, but theoretical limit, I don't know, is the answer, sorry.
Okay, on that note, could you please join me to thank Maria for a fascinating talk?